Deep dive into scikit-learn's Gaussian process classifier. The Gaussian process classifier in scikit-learn provides a powerful tool for probabilistic classification using Gaussian processes. This model is particularly suitable for situations where data is complex and nonlinear. Gaussian processes can capture intricate relationships between features and the target variable. Uncertainty estimation is crucial. The model provides probabilistic predictions, quantifying the confidence in each classification. Small datasets are available. Gaussian processes can effectively generalize with limited data. Here's a comprehensive breakdown of the Gaussian process classifier and its workings. 1. Gaussian processes. The foundation. Definition: a Gaussian process GP is a collection of random variables, any finite subset of which has a joint Gaussian distribution. In essence, it defines a probability distribution over functions, allowing us to model the relationship between input features and target variable as a smooth, continuous function. Key components. Kernel function. This function defines the covariance between function values at different input points. It dictates the smoothness and complexity of the learned function. Popular kernel functions include radial basis function. RBF captures smooth, localized relationships. Linear kernel represents linear relationships between input features. Polynomial kernel models polynomial relationships. Mean function represents the prior expectation of the function, often assumed to be constant. Advantages. Flexibility: can model complex, nonlinear relationships. Probabilistic predictions provides uncertainty estimates for predictions. Smoothness: learned functions are typically smooth, avoiding abrupt changes. 2. Gaussian process classifier utilizing GPs for classification. Underlying mechanism: the Gaussian process classifier employs a probabilistic approach to classification. It leverages the posterior distribution over the function to estimate the probability of a data point belonging to each class. Steps. 1. Training: the model learns a GP based on the training data. The kernel function and hyperparameters are optimized to maximize the likelihood of the observed data. 2. Prediction: for a new data point, the model predicts the probability of each class using the posterior distribution of the learned GP. The class with the highest probability is chosen as the predicted label. 3. Key parameters of Gaussian process classifier. Let's delve into the key parameters within the Gaussian process classifier constructor. Kernel specifies the kernel function used for the Gaussian process. As mentioned earlier, you can choose from RBF, linear, polynomial, and other available kernels in scikit-learn. The default is RBF 1.0, indicating a radial basis function with a length scale of 1.0. Optimizer controls how the hyperparameters of the kernel function are optimized. Options include FMINLBFGSB default, a quasi-Newton method for optimization. FMINNCG, another gradient-based optimization algorithm. None: no optimization will be performed. N restarts optimizer determines the number of random restarts for hyperparameter optimization. The default is 0, which means no restarts. Increasing this value allows for more thorough exploration of the hyperparameter space. Random state controls the randomness in hyperparameter optimization and initialization. Set it for reproducible results. Multiclass defines the strategy for multi-class classification. Options include 1. vs rest default trains a separate binary classifier for each class against the rest. 1 vs 1 trains a binary classifier for every pair of classes. N jobs controls the number of parallel jobs used during optimization. Set it to -1 to use all available processes. 4. Key methods of Gaussian process classifier. Fit X. Y trains the model on the training data X. Y. Predict X predicts the class labels for new data points X. Predict Prob X predicts the probability of each class for new data points X. This method is useful for obtaining uncertainty estimates. Score X. Y evaluates the model's performance on the given data X. Y using the chosen metric, e.g. accuracy. 5. Example implementation. Python. From sklearn, datasets import load iris. From sklearn, model selection import train test split. From sklearn, Gaussian process import Gaussian process classifier. From sklearn, Gaussian process, kernels import RBF. Load the iris dataset. Iris load iris. X iris. Data. Y iris. Target. Split data into training and testing sets. X train. X test. Y train. Y test train test split X. Y. Test size 0.2. Random state 42. Define the kernel. Kernel RBF length scale 1.0. Create the Gaussian process classifier. GPC Gaussian process classifier kernel. Random state 42. Train the model. GPC. Fit X train. Y train. Make predictions on the test set. YPRED GPC. Predict X test. Evaluate model performance. Accuracy GPC. Scores test. Y test. Printf accuracy. Get probability estimates. YPROBA GPC. Predict prob X test. Printf probability estimates YPROBA. 6. Considerations and best practices. Kernel selection. Choosing the right kernel function is crucial for successful GP modeling. The choice depends on the expected relationships in your data. Hyperparameter optimization. Optimizing the kernel hyperparameters is often essential for good performance. Utilize the optimizer and N restarts optimizer parameters to find the best settings. Computational cost. GP models can be computationally expensive for large datasets. Data scaling. Scaling features to a common range can improve optimization and performance. 7. Conclusion. The Gaussian process classifier in scikit-learn provides a valuable tool for probabilistic classification, particularly for complex, nonlinear data. By understanding its underlying mechanisms, key parameters, and best practices, you can leverage this model effectively for tasks requiring uncertainty estimates and robust generalization. Remember to consider its computational cost and the importance of carefully choosing the kernel and optimizing its hyperparameters.